So this is the third talk of the day, and I'm not even going to try pronouncing your name. So will you please give Mr. Jurovic a round of applause?
Thank you very much. Can you guys hear me? Can you guys hear me now? Oh, awesome. Can you guys hear me now? It's very loud? Sorry. It's okay. Oh, now. Wow, okay. This is gonna help a lot because I usually speak very quietly, so I love the fact that this is here. Maybe even a bit too much? Okay. Better? Okay, good. Thank you very much. And thank you all for having me. Yes, my name is not easy to pronounce. It's Mateusz Jurewicz. And today I will be talking to you about machine learning. So without further ado, first I would like to explain why I'm even giving this talk. I think machine learning is a field that is still, in certain ways, in its infancy. And I think it needs people who have expertise in other areas, both engineering and other. So I'm doing this presentation in order to make it much easier for you guys with your expertise in your fields to contribute to the field of machine learning. And even though the presentation is just a small part of that, there's also a larger project which I will point you to if you ever want to seriously get into the field, get all the resources, tools, and courses and how to do that. So what we're going to be doing today is first I'm going to talk about how the machine learning actually happens. I want to give you the basic idea of how machines can even learn. And there's going to be a bit of linear algebra there. I hope that's okay. This talk is meant to be for anyone, even if you don't have experience in programming or engineering or mathematics. So if you do, bear with me or feel free to correct me if I get something wrong. But we have to build that foundation first. Then we're going to jump from the presentation into a Jupyter lab, where I will show you in code how we achieve this thing that you probably you've seen somewhere, where we take a picture and we take the style of a painter and we change that picture so that it looks like Van Gogh painted it. Okay? And then if we have time, we're gonna do a brief overview of other branches of machine learning so that you know what else is in the field that might interest you. And then I will provide you the resources for actually getting into machine learning, like dipping your toe and checking if this is something you want to do. And then I understand there's going to be a Q&A. Okay? So guys, like I said, this project is a bit bigger. The thing I really want you to check out is this repository on GitHub. You can see here examples of this style transfer that I mentioned. You're going to find both a Jupyter notebook and Python code for running it on your own images. So you can just experiment with it, play with it if that's your way. But you will also find many other resources there. And don't worry about writing this down now. If you remember my impronounceable name, you can just find it on GitHub this way, or you can write it down when we do the Q&A, because this slide will be up. Okay, so first thing that we need to figure out is how machines represent concepts that are actually useful to us. For those of you who are familiar with this, bear with me, the learning curve will be steep at a certain point. So essentially first we have a scalar, which is just a single numerical value. But even this extremely simple thing can represent a lot of useful things, technically. If it's an 8, it could be obviously values on a scale of 0 to 9, or it could be which of the digits am I holding up in a picture, technically. That could represent that. Then there's a vector, which could be, for example, 3 users rating a movie, or it could be one movie on 3 scales. For example, the first one could be how much horror is in that movie. The second one could be how much comedy is in that movie. The third one, how much romantic elements are in it. I'm just trying to kind of show you that there's great flexibility in what we can represent with these simple data structures. Then there's a matrix, which is really just a vector of vectors. This could represent 3 different users' ratings of 3 different movies. Because this is a bit clunky, we actually usually, notation-wise, show it like this. And this can also be a grayscale image, technically. Again, this flexibility comes to mind. Then there are tensors. Tensors have a pretty specific mathematical definition, but that's a bit too nuanced for us right now. So think of them just right now as a vector of matrices. Technically, scalars, vectors, and matrices are all tensors. So from now on, when we talk about this, we're going to be talking about tensors. And this is also where the popular Google library TensorFlow takes its name from. You can also imagine that tensor that we just saw as essentially a cube. And if we can imagine it as a cube, we can imagine it as a 3D shape. So it can be the same image in 3 different points in time, or it can be the image and its mood and its motion. There's just this like great flexibility in what we can represent with these tensors. Okay, but that's obviously not enough. We need to transform them in some way. Mathematically, what we usually do with these tensors is matrix multiplication, also called their dot product. So here we have a very simple matrix multiplication example, 2 tensors, both of them 2 by 2. We could be tempted to multiply them just element-wise, you know, that 1 in the top left corner multiplied by that 1 in the top left corner of the other matrix, and that's the top left corner of the final one. It's actually a little bit more involved. It's technically multiplying the internal row and column vectors. You don't need to, if you don't follow, it's okay. The reason why I'm showing you this is just because I wanted to show you that this operation, which is very key to what we're going to be doing in machine learning, is actually a more deeply intertwined way of combining tensors. And we do the same thing for every single cell. Now, you probably heard the term, hello, you probably heard the term neural networks. And since I'm trying to demystify a lot of those terms, a neural network is really just a bunch of operations like the matrix multiplication stuck together with some bonus stuff that is changing the way it behaves. So I now have to talk about neural networks a little bit. This is a very simple diagram of a neural network. Okay? Everyone still with me so far? Okay, you're nodding. That's good. So the people at home, they're nodding. Right. This is a very simple example of what a neural network can look like. We have input, and this is literally just 4 numbers here. So you could imagine this input as being, in that topmost cell, a person's age. The second one could be their salary, and then their marital status, and so on. Things we can represent with numbers. The first layer of the neural network, which does the matrix multiplication, is actually both those black lines and the purple dots that come after them. The black lines is the actual matrix multiplication. The dots are the output of that operation. So one important thing to remember, net layers in a neural network have both an operation and an output. And this is going to be crucial when we do neural style transfer. So yeah, we do this a couple of times. We know that because of how matrix multiplication works, it's no longer commutative, so order matters, and there are certain limitations on the shape, but those are all nuances. And in the end, one more dot product, one more multiplication, and we get the output. And the output could be 3 zeros and a single 1. And depending on where the 1 is, that encodes something. For example, should this person be granted this insurance rate or not? I promise this is the last deeper detail that we need to understand. Other than the matrix multiplication, which we do here in this black network, this is the matrix that is the input. The matrix by which we multiply it is called the weights or parameters of that layer. And this is going to be the thing that we're going to be changing when we train the network. We also add a bias vector, just so that the function can take any linear shape. And then we add a nonlinear transformation. And we add the nonlinear transformation, for those of you who know, like a sigmoid function or a softmax function, because if we didn't, if we just did a series of matrix multiplications, we could only have this model resemble linear functions. And this is really why the metaphor of neural caught on, because this is the single behavior that resembles how neurons actually work. Unless the action potential of the neuron is reached, if it isn't, it doesn't fire. If we cross the threshold, it does fire. That's what the nonlinearity does. Okay, I know that's a lot to throw at you. This is the output of the Keras library's plot model function. This is an actual model that you could use for certain simple tasks. I'm showing this to you because I want to show you that there really isn't that much more to this other than those stacked mathematical operations. Okay? So here we have an input layer on top. We have a 2D convolutional layer, which is the last operation I will have to explain. And then there's max pooling, which just reduces the number of parameters we have to learn. And there's a flatten, which turns a matrix to a vector. And then there's a dense layer, which just does what I just described. So there's no magic, technically. This is convolutional layer. This is going to be important because convolutional layers are great at doing stuff with images. And this simple animation is supposed to show what it looks like. So the blue tensor on the bottom is the input. The green tensor above is the output. And what the convolution does is it just walks over the output in tiny steps, combines the numbers that it grabs from the input with the values of the gray filter. So again, just two matrices, two tensors, combines them together, and then outputs them into the input. To be more precise, here we have on the left the input, on the right the output. So you walk the input with this little filter, and you can specify the size of the filter, specify the steps, and you combine essentially all the values around the little cell, which ends up with a new value in the new image, which is the output of that layer. Okay? So in the dense layer, we were learning what the parameters, what the matrix that we multiply stuff by is. Here we're going to be learning what those numbers are supposed to be for a useful representation later on. Again, to drive this point home, this is an example specifically. If we use a filter like this, with just these values, if we convolve with this filter over the original image, we're going to get this output image. And this is a sharpened filter. And there's a lot of these simple filters. If the values were different in this filter, they could very easily recognize edges in an image, like this, edges like this, diagonal, and so on and so forth. Now, what do you think will happen if we stack a couple of those convolutional layers on top of each other? Does anyone have a guess? Well, if we can learn about edges or a sharpened image in the first layer, then when we combine them, we start with edges. This is like very early convolutional layer in the model. We pass the image in. It walks over the image. It learns, and I will explain how it learns in a moment, but essentially it learns these simple patterns like edges. In the next convolutional layers, it will learn combinations of those. Because these are, what I'm presenting here are outputs of those convolutional layer that would excite them the most. Then we get textures. A couple of layers after that, we get patterns. You can see here, I think, almost like stubs from concerts and such. Then you get parts. You see something that looks like an interface in the top left of the second panel there. Something that looks like dog's ears, maybe denim. And then finally, we get to a point where the convolutional layers stacked together learn actual objects. So architectural stuff. Here we see someone's shorts, I think, eyes, insects, and actually heads of dogs. It looks weird because they don't know where something might be. So they kind of look for the thing everywhere in the image. But this is one thing that I need you to remember for the neural style transfer to be clear to you, essentially. Early layers of a convolutional model, simple aspects of the image. Later layers, things that are actually in the image. Okay, so yeah, now I've told you kind of what the inner workings actually are, but I haven't told you how learning actually happens. So let's do that. To simplify, let's imagine our network, our model, as just some input, some transformations, some output. In order for learning to happen, we need to know how well we are doing for the simplest possible type of learning. So usually we feed the network a lot of data where we know what the target is supposed to be. You know, remember those 4 reddish dots at the end? That's still just numbers, that's still just a vector. And we know what the target vector is supposed to be. So for example, a vector with 4 elements, all of them zeros except for the last one, which is a 1. And we know that that encodes, for example, a dog. The last index encodes a dog. If the 1 was in the 3rd index, it would be a cat. Second one, parrot. First one, rat, for example. And then we know what the target vector would have been. And it was actually a picture of, let's say, a cat instead of a dog. And then we can just do a mean squared error on those vectors. This is obviously a very simple example, but we can say that those vectors are not the same, and we can describe it mathematically. So the only catch is that this loss function, which we will be trying to minimize during learning, has to be differentiable, which just means that, most of you probably know, we just need to be able to tell what will happen if we change the parameters a little. Does the value of the function go up or down? And this is really the trick to learning. We keep the entire model differentiable so that we can figure out if we change its parameters a little, will we get a lower or a higher loss function? And we obviously want our loss function to be as small as possible. Are we all on the same page so far? Okay. So final bit of linear algebra, backpropagation. So we know that the model has to be differentiable. How do we use that? I'm going to just stop it for a moment. Or am I? Yeah. Okay, this GIF is just going to keep rolling. Bottom, we have the input. Top, we have the output. It goes through the entire network in one forward pass, gets to the top, calculate the loss function there, and then we begin to check the derivatives. So we check how we can change the values of those parameters to make the loss function go up or down. And this is what we use to then update the parameters of the network. And that's how learning happens. As a tiny bonus, I just also wanted to tell you what recurrent neural networks are. You may have heard about them. And I just wanted to, again, demystify them a little bit. Same function, graph of a network. Recurrent networks are great at figuring out what is happening in a video or in a larger block of text because they have some representation of what was important earlier on. So you can see here the second layer called long short-term memory. Some of its output is kept untransformed until a couple of transformations later. And you can this way have some information about what was happening earlier in a video or earlier in a text and use it later. Okay, now you may be wondering why there's a duck here, and this will become clear in a minute. Can you see this? Probably not. Is this a bit better? Can you see? Bigger. Can I do what? Full screen Chrome. Yeah, let's check that. How do I do it? Green button thingy. But this is it, right? This is the same thing. Cool. Okay. So guys, in my personal experience, the presentation would just show you line after line of code are not that useful. You either way have to be able to follow it, on your own at your own time. So I won't be explaining everything, but we will see this specifically do the thing it's supposed to do, and we will see the output of it. How many of you are familiar with Python? Could you raise your hand? Okay, so vast majority of people. Good. Even if you're not, that's okay. I will be explaining what we're actually doing. So I am just importing a couple of libraries. I am importing TensorFlow, which is what is going to be doing the heavy lifting. I'm importing Keras, which is a high-level API for TensorFlow. So if you're interested, you're probably going to be doing things in Keras first, and just a library for manipulating images and a library for operations on tensors, on linear algebra stuff and numbers. I'm grabbing some functions, simple functions that I wrote for loading images. This is something that I would like to see more of in machine learning papers. Confirm in the notebook that you have all the right requirements. And we're going to be using Python 3.7. And these are all the libraries that we're going to need underneath the hood in the virtual environment for this working. OK, so I was originally going to have us choose which images we're going to mash together. And I'm going to be here after the presentation for a couple of hours. So if you're interested, we can do that. But just for this example, I'm going to use these two images. OK. So this is a majestic horse duck on the left that some person with great Photoshop skills has created. And on the right, this drinking is tricky with this. And on the right, you can see an image in the style of Salvador Dali, not actually created by Salvador Dali. And what we're going to be doing is we're going to be trying to make this image on your left take the style of the Salvador Dali image. And you can see there is a style to Salvador Dali. It's very highly saturated. There's great contrast between colors. There's edges between objects, but not edges like the gradients are very smooth in this image. We're going to be loading up the weights of a specific model that was trained to recognize what an image is, what specific images are. There's a competition in machine learning called ImageNet, and this is a model that won it a couple of years ago. It's often used because it's fairly simple. We just need it because when you think about it, remember those panels I showed you of edges and patterns and then objects? That knowledge is encoded in that model now, and we can actually use it in a clever way. We're going to be generating an image. Here are some parameters for learning. Often in practice, when you do machine learning, you have to fiddle with certain parameters for learning, such as how many times I want it to mull over the data. In our context also, how much do we care about the contents of the image, and how much do we care about the style of the image. And these are going to be used, you can probably figure it out, when we're going to multiply them by different types of losses in a moment. OK, and this is really the gist of it. So you remember the image that I showed you with what the network learns in the early layers and what it learns in the later layers, right? When you think about it, those edges and those simple patterns, they are kind of like the style of an image, a little bit. For example, when you think about paintings by Kandinsky, there's like a very specific brush stroke there. So what we're going to be doing is we are going to be considering the output of this pre-trained model from the early convolutional layers to be essentially the style of an image. And we're going to be considering the output of this model from one of the later layers, where we saw them learning things like objects, to be content, right? This is really the one trick we have to wrap our mind around. You know, I hesitate to go back to it, but I feel like you're no longer with me a little bit. Are you? You are, OK. Good, sorry. So yeah, we're just going to be grabbing one of the later layers for content, and we're going to be grabbing the output of two early convolutional layers and one of the later ones, because that seemed to work better. And yeah, and we're just going to be treating that as content and style. There's a couple of functions we need to go through very quickly. Getting feature representations is just about figuring out what the content and the style of an image that we pass to this function actually were. So we just load up the content image, we load up the style image, we pass them through the model, and then we grab the outputs of specific layers. Since this is machine learning, we have to specify a loss function. And we're going to have two of them, because we want to do two things. We want the model to have same content and same style. So how do we do content loss? Well, we have the outputs of the model for the content convolutional layers, for both the image whose content we're trying to keep and the image that we will be changing during learning, the image that we're generating. So then we can just do a simple mean squared error, really, because that's just how similar two tensors are. No magic there. With the style loss, we're doing essentially the same thing, except for one nuance, which is a gram matrix transformation. A gram matrix transformation is essentially you flatten a tensor and then you multiply it by its own transpose. Really, from what I understand, the authors of the original paper that this is based on, which I also linked to in the GitHub, they didn't have a clear idea of why this worked so much better, as opposed to just, using the raw stuff. I think recently there was a paper that explains mathematically why it actually learns better. I haven't read that one. I think this is a bit of a shameful thing that happens in machine learning a lot. We sometimes don't know why things work, but they work. So if you're interested, I can look up that paper for you. And yeah, this is just the gram matrix transformation that I just described. And what we do is we just, again, get the generated output of those specific layers for both for the image that we will be training and changing, we will be changing during training. And we only once have to pass the style image and the content image through the network to get the outputs that we know we actually want. And we're trying to make the outputs from the generated image be as close as possible to both of those, essentially. This is just for unpacking because we've used multiple layers. And then we multiply, we get one total loss by multiplying those individual losses by the amount of style that we wanted to keep and the amount of content we wanted to keep. We load up our model, and this is the important part. We don't want it to be trained. The model is trained as it is. It contains some knowledge. We don't want to touch it. So we tell it specifically that we don't want to train it. And we also define which layers outputs we are interested in. Then we just start a TensorFlow session, get the model, get a lot of warnings. And then we compute the style features and the content features. And we turn the style features into a gram matrix. There's a little bit of pre-processing that we have to do, just because when you think about it, when we do data transformation, we usually want our input to be in the same range, so we have to normalize it. But then the specific normalization parameters depend on what corpus of data you passed to it originally. So we are a little bit tied to the images that were originally passed to this network when it was trained. The generated image starts out as just the content image, because we're just going to be making changes to that one. We pack our style and content weight into one variable. We define the loss as we have already. And this is the final bit of magic. We use a solver function from TensorFlow, here the atom optimizer, and we tell it to minimize the loss. We're going to be outputting both the total loss and the style loss and the content loss. So we're just trying to make it minimize the total loss. And the only thing that it can change, the only thing that we're telling this function to be able to change is the actual image. So it's not making changes to the weights of the matrix. It's just going to be adjusting that very image. And we give it a learning rate, which just means how much can I change the image by at every step. We have to reload the weights because of TensorFlow. And yeah, and then we're just going to run it for a number of iterations. Yeah, it has to check whether the values of the image are good, but that's a nuance. And yeah, it continues running the optimization operation and it computes the loss. So I'm just going to run it. And then it will crash and burn, possibly. We're just going to hold here for a moment so that we can see that it actually does something. OK, it does something. And we're going to come back to this at the end of the session to see what it does. How do I get out of Chrome presentation? Exit full screen. OK. I realize it may sound like magic. I hope it sounds less like magic, but I realize it can still sound a little bit like magic. If I still have time? Perfect. I just want to tell you a little bit about different branches of machine learning. It's going to get a little esoteric now and a little bit more general, and I actually hope maybe more interesting for you. Some of it is going to be speculative. OK, so first branch of machine learning that I want to talk to you about is, other than the ones I already have, is reinforcement learning. Reinforcement learning is just the model is actually an agent in a specific environment, and it makes decisions within that environment. Yeah, and a demonstration here. Maybe some of you have already seen it. This is AlphaGo, AlphaStar that beat StarCraft to the best players. Before I play the clip, for those of you who don't know StarCraft, it's a real-time strategy game. The AI is controlling the blue guys here. And these are units that have one specific ability. They can teleport at very short range. And they have shield and health. And if they lose shield, but then aren't in combat, they regenerate the shield. So the shield is a resource that can be managed and regained. And this is the human player, and let's just see how he fares. You can see that the AI went with a fairly uniform strategy here. It's just spamming those units with that one ability. What the human player is doing is usually considered a hard counter to that build, Immortals and Zealots specifically. So if these were two humans, we could expect the red one to win. But you can see that it does this thing where it keeps the wounded, it teleports the wounded ones immediately to the back so that they can still keep outputting damage even though they are not technically taking damage. And this is kind of impressive, right? It's like, maybe it's like simple resource management, but quite a elaborate thing to learn, I think. And yeah, just to explain what is actually happening there. Still, this simple model of input, transformation, output still applies here. It's just that when we pass input to the model, we pass the current observation about the environment. And you can actually argue that the guys who made AlphaStar were cheating a little bit because the algorithm could always see the entire board, where humans usually have to zoom in and manage the little window. It sometimes can also get the possible actions. When you think about the AI playing a game like Mario, the possible actions are always the same. You can jump, go left, down, so on. But sometimes in more complex games, certain actions will not be possible, depending on where you are in the environment. What it learns is considered a decision policy. So this is the state of the environment. How do I make those decisions? And the output is the chosen action, and then we get the next discrete step of the interaction with the environment, really. And we have a reward function. It has to want something, usually maximize points. And we can sometimes see interesting things here, such as it learns to play the game in a way we didn't predict. It finds bugs to maximize points, which we didn't see earlier. OK. Generative learning is a type of unsupervised learning. This is when we usually feed the algorithm a lot of data from a specific sample, and we want it to generate a lot of data. And we want it to generate new samples from that set. So for example, you could imagine that it wants to, we give it a lot of paintings by Salvador Dali, and we want it to output new paintings by Salvador Dali. Sometimes we give it random input, which is when we want novelty, so that it doesn't just output the best, most Salvador Dali picture ever. Sometimes we give it more specific things. This is, for example, from a paper where machine learning engineers taught the algorithm to generate pictures that match the content of the image. Here, a red white bird with a very short beak and a strange number of legs, but still. There's a specific type of generative learning that I want to talk about that you may have heard, generative adversarial network. This is when we technically have two models. One is called the generator, and it does essentially the thing I just described. It tries to generate new samples from a corpus of data that match that corpus, that are very similar as the data that was fed to it. And then there's a discriminator network, which essentially has one job. Is this a fake sample, or is this from the original set? And through a little bit of clever gradient juggling between the two, you can actually make them bootstrap each other. They get better. As the other one gets better, the other one gets better, and so on. Better fakes are generated. You have to be a better discriminator to get a higher reward, and that's how it happens in a loop. One important thing I want to talk about also is federated machine learning. This is hopefully a way for us in the future to have machine learning that is more privacy-based. This is where the training doesn't happen in a data center somewhere. It's supposed to happen on your device. This is a picture outlining the entire protocol that Google recently came up with. I think it's a step in the right direction. You can see here that the training happens, I can't see my cursor anymore. The training happens on the device. This is all the stuff that happens on the device, and this is the stuff that happens in the data center, in the cloud. It's a very good protocol, I think, technically. I have personally certain qualms about it still, but if you're interested, you can just look up federated learning. And finally, the most controversial topic within machine learning. AGI is artificial general intelligence. This is a still from one of the movies, Blade Runner 2048, that recently touched on this subject. What is an AGI? It's meant to be a model that is as flexible at learning different things as essentially a human mind. So like a human level intellect. We seem to be very intrigued by this concept in culture. We've seen it in Star Trek, Blade Runner, we've seen it everywhere, pretty much. Terminator, famously, obviously. Most recently, the movie Her and the Blade Runner sequel. There are two interesting metaphors that are usually used when discussing this, and again, I'm prefacing this by this is all highly speculative, although I am going to point to specific research within the subject. One is that of an oracle, which is essentially we have that model that has learned so much knowledge, but it is locked in a cave or a cage, so the only way we communicate with it is through some sort of text communicator. It has no agency in the world. Or essentially, the ominously sounding deal with the devil metaphor, which is we expressed a wish, and then the AI agent acts in the environment and tries to make our wish happen. And this is obviously from Dr. Faust. This is Mephistopheles. And this is a good example of a perverse instantiation of the wish. You may have heard about the paperclip maker example. We tell the AGI, make paperclips. It proceeds to make paperclips until there's no more universe left, essentially. So you can see kind of that we've been playing around with these metaphors and these topics for a while in culture as well. But there are specific research problems that are being addressed within this field. One of them is the orthogonality thesis. The orthogonality thesis, which I would think we really need to come up with a more human understandable name for it, it just means that any level of intelligence is compatible with any goals. We may have this intuition that if a person or if an intellect is very intelligent, they will also, by consequence, be good or virtuous. And this thesis states that that is not true. Once again, you can have an extremely intelligent paperclip maker. It's difficult to prove this in formal logic, but yeah, efforts continue. And if it is true, then we should obviously take certain security countermeasures, shall we say. The concept of instrumental goals, it's just that no matter what end goal you give it, largely, it's probably going to converge or getting certain things regardless of that goal. So money is an instrumental goal, power, sometimes fame. So you can get a sense that whatever the goal you give it, even if it's virtuous, it will probably want to have as much power as possible because that increases the likelihood that it will achieve its goal. And finally, there's the caging problem. You can imagine a scenario where somehow we've built the oracle and it's virtuous. How do we keep it in a cage? Well, maybe this will happen at some big corporation's data center. And you would imagine that, okay, so those servers are somewhere unconnected to the internet, perhaps, so we're safe. Problem is, if we did that, then if it's really intelligent, then it could manipulate its internal processing so that the electricity that happens within the servers can technically be used as radio waves, and then it's no longer contained. So I'm just mentioning this because there's a lot of interesting, cool problems here that sometimes go against our intuitions. Yeah, let's check out how the horse duck worked. Yes, we need it bigger. There. Okay, so it prints something out every 10th iteration. So you can see the original image, lots of texture here. the style image. And even on the 10th iteration, I'm just going to make it a little bigger if I can. I can't, sorry. Yeah, that size is prefixed. But yeah, you can see that lines are getting smoother, the colors are getting more saturated, there's almost like a rainbow in its tail. The clouds look different. All of a sudden, the tree has grown a leg and looks vaguely like a bird. And the colors are getting more and more vivid. And we see a much more vibrant dark here. And the grass doesn't look like grass anymore. And yeah, we can see that our little model has learned to make a better combination of those two images. I'm going to stop it now. I'm just going to interrupt the kernel. And I am going to show you the final output after about 200 iterations, just so you see how it looks like. Yeah, you can see a certain loss in fidelity, but what do you think? Did it capture the style of the eye? Okay, great. So guys, I'm just gonna hop back over to the presentation. Well done, well done. Thank you. Okay, so thank you so much for your attention. I know that this was a bit of a, yeah, like the title said, a crash course. It's a lot of subjects, but yeah, we talked about how learning happens, gave you an overview of the other branches, and I would like to deeply encourage you to hop over to this project on GitHub. It's not just my work, we did it in collaboration with a couple of people who are passionate about making it easier for people who are new to this topic to just hop on over. So different courses that we've all done personally, different books, tools, scientific papers, blogs that you might want to follow, YouTube channels, and so on and so forth. Yeah, just hop on over and see what you can do, because we really need people who have your expertise, people from all sorts of fields. Thank you very much for your attention.
Any questions? We're not gonna bite you if you say yes. Yeah, a question.
Well, you can hear me. Yeah. I was interested with the ethical themes that you touched on at the end. How do you feel that they reflect in the lower level work? I mean, the scripting and the coding. So when you're interfacing to the TensorFlow, for example, do you ever think about those things when you're actually programming?
I think we definitely should. Great question. First of all, this is something that is very close to my heart. One of the resources that I've included is actually an ethics guidelines from the European Union about this. To give you the most honest answer, I don't think it's as often on my mind as I wish it was, but that is a little bit because of what I do specifically at my company. In private projects, more so. I think irresponsible choices creep in very early. Like, sorry, I'm exasperated with myself, not with you. You can make such an innocent bad choice that will have such dire consequences later on in this. Just choose the wrong data. Choose data that does not include people from, the end user group, really. Like, was it Apple's facial recognition stuff? Like little bits like that. Problems with data leakage. There was like one famous instance where someone claimed that they learned how to recognize the flavors of a sandwich by a picture. And it turned out when you looked at the data that the trays on which the sandwiches were put were of different colors depending on the taste. Like you can make such little mistakes that have such consequences there. And I'm not even getting into any of the like deeper, more forward problems with it. I think we definitely need to get much better at that. And I try to be mindful of it in my daily work, but yeah. Thank you, great question.
Any more questions? Let's have a big round of applause then.
Thank you.